Hi, welcome back to our exam review. This is the fourth video. We're looking at question number 5. This is from page 13. In 1978, researchers placed a group of 20 deer on a large island in the middle of a lake. The deer had no natural predators on the island. Researchers collected population data and created a graphical model. The researchers estimate that the island has enough resources to support a population of 320 deer. In what year will the deer population be too large for the island? Too large for the island. Okay, so for it to be too large, it needs to be a population of 320. Okay, so we need to kind of figure out when this is going to happen. Okay, we want to read the graph. It's probably going to be somewhere around 28 or 29. So let's draw a nice line going down. And this here is 30 on the graph. So we're probably about maybe 30 to 31 years. So we could say approximately 30 years. How many years did it take for the initial population to double? Okay, so that's part B. How long did it take for the initial population to double? So the initial population would be the value right here, which looks like it's 20. How long does it take to reach 40? Let's zoom in a bit more. We'll get a better value at that. So, okay, it looks like it happens at 8 years. So it takes 8 years to double. In what year was the population 100? So 100 is right here. And that's going to be about right there. So 18 years after 1978. So 1996. How many deer were on the island in 1994? Well, 1994 is just 2 years before 1996. So 2 years before that would be at the 16 years after 1978. And it looks like there is 80. Okay, next question. So in this one, it says, in each case, write an equation that models the situation described. Remember the general form of the exponential equation, y equals a times b to the exponent x, where a is the initial value and b is the growth and decay factor. So it says an antique is purchased for $5,000 and appreciates by a value of 3.25% each year. So we're going to write this. The initial amount is 5,000. The growth factor, now here we have to be a little bit careful, okay? For there to be growth, the base has to be greater than 1, okay? This is a percentage. This is always needs to be converted to a decimal. Okay, that means we got to move this over 2 to the left. So we get 0.0325. Notice this is a lot smaller than 1. So in order to get growth, this has to be added on top of 1. Okay, so we have to do 1 plus the growth percentage. So it's going to be 1 plus 0.0325. Okay, so whenever you're given growth percentages, when we convert that percentage to a decimal, we always get a tiny number that's less than 1. But if it's growth, what we do is we just take this and we just add plus 1 to it. And that's the value that we need to use for the base for our exponential function. Okay, and then x would just be the exponent. So I don't really want to leave it in this form. I'd like to simplify that, so we should just write it as y equals 5,000, 1.0325 to the exponent x. Okay, and that's our final answer for that. All right, let's do the next one. A town had 2,500 residents in 1990. It grew at a rate of 0.5% per year for 2 years. So we would have y equals 2,500. The growth rate is going to be 1 plus, I'm going to move this over 2, so 0.05 to the exponent x. Actually, it says t here, so I should use t. So just cleaning that up a bit, I could probably write this as 2,500, 1.05 to the t. So y would represent the population of residents from 1990 on. Okay, the next one. The value of my car was $25,000 when I purchased it. The car depreciates at a rate of 25% each year. Depreciate means that it goes down. It's not going to be a growth, exponential growth model. It's going to be an exponential decay model. So the initial amount is 25,000. Instead of doing 1 plus the percentage, we're going to take the percentage away. Let's move that over 2 decimal places. So we're going to have 1 minus 0.25 to the exponent x. Okay, and we should just simplify that in our last line. 1 minus 0.25 is 0.75. Okay. See how that works out? By doing 1 minus, whenever you have decay or depreciation, you should be using a subtraction. And my base ends up being smaller than 1, which causes the decay. So the only reason why we're adding 1 or doing 1 minus is because these questions are all giving us percentages of growth. Okay, so whenever you get in percentages, you're always going to want to do either 1 plus or you're going to want to do 1 minus. If it's growth, add them. If it's decay, subtract them. A single bacterium of a particular type takes 1 day to double. The population is P after T days. So they're telling us they want to see is P and T. So I'm going to write this as P equal to, what's my initial amount? Well, it says single bacterium, so just 1. And it takes 1 day to double. Okay, so this isn't a percentage. This is telling us that it doubles. That's my growth factor times 2 each time. So I'm just going to put 2 in here. And then we add the exponent t. So after 1 day, we would put 1 in for t, and we would have 2, and so forth. All right, now we'll probably just do one financial question here. You can expect to just see 1 on the final exam. Nothing too difficult. So just something calculating interest. So let's do this one here. This is definitely an appropriate one to tackle. So it says Jay has $2,000 to invest in a compound interest account, which he would like to leave the money for 3 years. He considers 3 different compounding periods. Option A, 8% compounded annually. Option B, compounded semi-annually. And then option C, compounded quarterly. Notice the rates are the same. They're all just compounding at different frequencies. So this is definitely a good question to practice. So for each option, what is the amount at the end of 3 years? So we're using this formula. Okay, and notice it looks like growth because we're doing 1 plus the interest rate. Okay. So this is the amount. This is the initial investment. Sometimes we call this the principal. That's the interest rate. And this is the number of compounding periods. Okay. These always need to be in the same frequency. So the interest rate, I, which is going to be written as a decimal. It always needs to match up with the compounding periods. All right, let's do option A first. So we have A equals our initial amount, 1 plus I to the n. The initial amount is 2,000, 1 plus I. The interest is 8% per year, so it's going to be 8% as a decimal is 0.08. Okay, and it's in for 3 years. We're told it's compounded annually. That means once a year. So if it's in for 3 years, it's just going to compound 3 times. Okay, put that all in your calculator. 2,000 times 1.08, because we're going to add them, and that's going to be to the exponent 3. Okay, not bad. $2,519.42. Okay, for option B. So it's going to look very similar. Okay, the only difference is this time the interest is compounded semi-annually. So if it compounds semi-annually, I need the percentage to be semi-annually, not yearly. Notice this slash A, that means per year. So I don't want 8% per year because it compounds semi-annually. I need to make it on a semi-annual basis. So if it's going to compound halfway through the year, I should probably find the interest rate for half the year. 8% is for the full year. Half the year, it's just going to be 4. So we're going to have 2,000. We're going to do 1 plus the 0.08 over 2. So I'm dividing it by 2 because it's semi-annually. I'm going to have half the interest rate. And the number of compounding periods, well, it's for 3 years, and it's going to go twice a year. That's a total of 6. Okay, so it's funny, if you notice a pattern with these, that 6 comes from 3 times 2. Because it's 3 years, and it's compounded twice a year. So if we divide the interest rate by 2, we got to multiply the number of years by 2 also. So whatever we divide the interest rate by, we're multiplying the number of years by. That's kind of a good way to look at that. All right, so this one will be pretty close. Okay, I'm just going to use a bracket. We got 1 plus 0.08 divided by 2. Close the bracket. That's all raised to the exponent 6. Okay, $2,530.64. Okay, why is this one a little bigger than the last one? It's about like $10 more. Okay, not that much more. Why is it a little bit bigger? It's because in this option, because the interest is being compounded twice as much because it's semi-annually, compounds 6 times instead of 3. When we compound an investment, what we're doing is we're taking the initial investment plus the interest it earned, and we're calculating the interest on that. So the interest is added in a little bit more frequently with this one than it is with that investment. So this extra $10 is basically the interest we made off the interest. Okay, this one collects interest off the interest 3 times. This one collects interest off the interest 6 times. So it makes a little bit more interest on the interest. That's it. I know that might sound really confusing, but that's basically how it works. So those are 2 options. Based on this trend, I think the next one is going to be even a little bit better. So we'll go with C. Same formula. Initial amount is 2,000. Okay, this time the interest rate is 8% per year, but it's compounded quarterly. So we can't have per year anymore. We need per quarter. So we got to divide by 4. So we're going to take that 0.08, we're going to divide it by 4 quarterly. And then the number of compounding periods, quarterly means 4 times. So it's 4 times for every 3 years. total of 12. This time I'll change that to a 4. I'll go up there and I'll change that to a 12. And we get a little bit more. So we made a little bit more interest off our interest this time around. Okay. So it's not a huge difference, but this is only over 3 years. Over a longer investment, it can actually become pretty significant. Okay, for each option, what is the interest earned? Well, the interest earned is going to be equal to the amount minus the initial amount. Okay, so for A, the initial or the amount that we had at the end was $25.19.42. The initial amount was $2,000. So we could see we made $519.42. For B, we're going to do the same thing. So the final amount at the end was $25.30.64. Subtract the initial amount, and this one made $530.64. So a little bit more. And lastly, option C, the interest is equal to the amount minus the initial amount. $25.36.48 minus $2,000. So $5,036.48. So which one is the better option? Well, the one that pays you a little bit more interest, right? We made about an extra $18 on this one compared to the first option. So the more frequently the compounding happens, that basically means you're going to collect a little bit more interest off your interest. Okay. I think that's actually good enough for these. Don't worry about doing these two. Okay, we did cut our investment section a little bit short. Okay, some of these we've already taken care of, so we're going to jump over to number 5. Okay, it says sketch the graph of f of x equals 2 times sine x minus 60 plus 1 on the graph in Q2 in the sinusoidal section. So I'm just going to draw it off to the side up here. Okay. So with these questions, remember this is the amplitude. Okay, this is the midline. Okay, which is basically our vertical shift. Okay, and this is the phase shift. So if I want to graph this, first thing I should do is graph the midline. So right at 1. Okay, and then I should add in the amplitude. Okay, so my max value is going to be the midline plus amplitude, which is going to be 1 plus 2, which is 3. So there's a max at 3. And the minimum is going to be the middle minus the amplitude. So 1 minus 3, negative 2. So I'm pretty much ready to graph. I'll take care of the phase shift last. So I'm just going to mark off 1 full cycle, 360. There's 180. There's 90. There's 270. Okay, my graph always starts at the middle, the midline, and works its way up. This isn't the most accurate graph, but it works. Okay, there's my graph there. Okay, This phase shift right here means 60 to the right, so everything moves over 60 to the right. So I'll do that part in orange. So 60 is about right there. I move this point over to 60. This one's going to go over. This one's going to go over. They're all going to move over 60 degrees. I know you guys remember doing these in class. So the graph would then look like this. Okay, that's how we do the graph. All right. Okay, let's now look at this one here. Also important. Okay, how many cycles are in this graph? So let's first read up here. So it says the following graphs state the number of cycles, the amplitude, the period, and the equation of the axis. When they say axis, they mean the midline. That's what I usually call it, okay, or the center line. So what are the number of cycles here? So we begin here, and then we go down, we go over, we go up. You might be tempted to finish it here, but it actually needs to come over a bit to finish the cycle. So this is one cycle here. That's one. This is the next one. And then this is the third one. Okay, and it actually is supposed to go over a bit more to finish. Okay, so what are the number of cycles here? It's actually not quite 3. This graph probably should have been finished a bit more. I'm going to say just under 3. Okay, that's probably a little bit of an error, whoever created this review sheet. So they probably meant for it to be 3 full cycles, but technically it isn't. Okay, so what's the amplitude here? So let's erase those. We don't need to see that anymore. Okay, to find the amplitude, it's good to draw a line through the middle. So the bottom is at 2, the top is at 4, middle would be right at 3. The amplitude is the distance from the middle to the top. Or you can even calculate it. You can do max minus min. Take all of that and divide by 2. So 4 plus 2 divided by 2. That's 6 over 2. That's going to give us 3. Sorry, it's a minus, not plus. 4 minus 2 divided by 2. So 2 divided by 2, and that gives us 1. Which makes sense because there's about 1 unit from the middle to the top. That's the best way to look at it. Okay, the period. So how long is one cycle? That's what the period refers to, the length for one cycle. So that's the period here. Okay, 4 units. What's the equation of the axis? So this midline I put through here, it happens at 3. So you could just say y equals 3. Okay, let's now look over, we'll do 2 and then we'll do 4. So it says graph sine x for the domain from negative 360 to 360. So we'll mark off the middle. And then we'll put our y-axis through that. So I'm just going to kind of label these in increments of 2, just to help me kind of see how many there are. So there's 1, 2, 3, 4, 5. 5 times 2 is a total of 10. Okay, so I could put positive 360 here, negative 360 there. So I know sine begins at the middle and then works its way up. So we'll mark that off as 1, 2, 3. Negative 1, negative 2, negative 3. Remember, sine is only between 1 and negative 1, like the base function sine x. Obviously, if there's transformation, that changes, but generally it always starts at the origin and then works its way up. So remember, I take 360 and I chop it in half and I get 180, and then I chop those in half and I get 90 and 270. So it's going to be the same on the other side. Okay, my graph starts at 0, goes up to 1, back to the midline, then down to a minimum, and then back to the midline again. That's general sine x graph. Okay, and then we go through like this, going backwards. Okay, so sometimes it's good to have this drawn first, and then you can do transformations to it afterwards. So like in this question in number 4. Just go back to your graph of sine x and sketch the graph of the function g of x that has been horizontally trended 90 degrees to the right. So everything's got to go 90 degrees to the right. Okay, and that's it. So everything moves over 90 to the right. 90 degrees is exactly 2 squares. So this moves over to here. This moves over to there. That moves over to there. You guys get the idea. Okay. So I have basically starting from there and going down. Okay, and it says go from negative 360 to 360. Well, that means I need to figure out what to put over here. Following the pattern, I know I should be at the minimum over there. So there's my graph for that. If I had to write an equation for this, I would write sine. And if it shifted 90 to the right, then I would write x minus 90 in the bracket. That shows a phase shift of 90 to the right. Remember, it's always the opposite sign for the direction that it goes in. Okay. We're going to skip number 5. Let's go on to number 7. So 7 is also important. Describe the transformations that have been applied to the graph of sine x to arrive at each of the following graphs shown below. So that's my amplitude. I can see the period stays the same. It looks like sine is starting at the origin, so no phase shift. So this looks like it's just been a vertical stretch by 3. So here I'm actually just going to state the amplitude. The amplitude equals 3. And that means the graph is now going to become y equals 3 sine x. Okay, this one over here. So this looks like the sine graph, except it's starting a little bit lower. And then the amplitude still looks like 1 because my midline is here. There's still 1 there. So it looks like it just shifted down. So my equation would be y equals sine x minus 1 unit. This is a shift, vertical shift down 1 unit. And I can tell because my center line or my midline is still at negative 1 instead of at 0. And the amplitude is still 1. So nothing changed that way. I can also tell the period, 1 full cycle is 360. So we didn't even change the period. Okay, this one here looks like just the amplitude changed because we're now at negative 1.5. Also, sine is supposed to start here and go up and then come down. So either there's been a phase shift or it's been reflected. I like to think of it as a reflection. So this one I would write minus 1.5 sine x. Okay, this is my amplitude, and then this shows the reflection along the x-axis. So we'll write that here, reflect along x-axis, and the amplitude is equal to 1.5. Okay, and for our last one, this has a period of 360, so nothing changed horizontally as far as stretches and compressions. Amplitude is still 1, so that's good. Midline is still at 0. It looks like it's just been a phase shift. So it looks like we went half of 60 degrees, so 30 degrees to the left. That means my equation is going to look like y equals sine. If I'm going to the left, it's going to be x plus 30. Okay, and that's it. So question 8 said state the equations for each one, and I already did that up above. Okay. All right, I think that is mostly it for our review. I'm going to have one more video showing how to evaluate some of the exponential expressions. So I'll see you in the next video.